And an incompressible fluid, this includes liquids only. Because if you have a gas inside of a chamber and you apply pressure to it, it changes the volume of the gas. But an incompressible fluid, almost all liquids are incompressible. Water is incompressible, oils are incompressible, almost every liquid is incompressible. And for all of those, Pascal's principle applies. And so this is a piston. We have a liquid inside of the piston. And if I apply a certain pressure, I have an area here. If I apply a certain pressure here, remember that my pressure is equal to force per unit area. So what that's saying is that I'm applying actually a force onto this piston, and then it's going down across this area. It doesn't matter how much volume of liquid is in the piston, it only depends on the cross-sectional area. That pressure that I apply up here is also felt down here. All right, the big application for this is a car lift or a hydraulic lift, which we've all had some experience with. I think we have. Actually, most of the lifts in your car these days are not hydraulic. Instead, they're like a screw-type mechanism. If you've ever changed a flat tire in your car, most of the jacks that you have in your car have a screw-type mechanism that lifts up your car. But it used to be that most jacks were hydraulic, that they actually had a piston inside of them that was filled with oil or some other liquid. By the way, do y'all know why hydraulic lifts almost always use oil? Any idea? Because you could use water and it's cheaper, it's less toxic. Why do they not use water? Wasn't it? Oh yeah, it would freeze. Is that really the reason? Who said that? Are you guessing? Okay, I think it's because it's corrosive. But yeah, it would freeze too. And oil doesn't freeze. It causes it to rust. Whereas hydraulic fluid is oil-based, doesn't. Okay, so in a car lift, for example, the input pressure is equal to the output pressure. And that's going to be sort of our equation for Pascal's principle, that the input pressure is equal to the output pressure. Because if I apply a certain pressure here, I apply a change in pressure here with a force per unit area, that pressure is felt all throughout this incompressible fluid. And that means that whatever pressure I applied over there, I'm also going to get over here. And so we can do something where we say that the input pressure, or I'll call it P1 in this case, is equal to P2. If that's the case, which it is by Pascal's principle, then F1 over A1 is equal to F2 over A2. So if A2 is bigger than A1 as it is here, then F2 is bigger than F1. So I can put in a small force and get out a big force. All right, so that might just cause your ears to tickle a little bit, because it sounds like in some way this device, this hydraulic lift, is actually giving us more work, that we're creating a force that's bigger than the other force, which in some way produces more work. And it just sort of seems to pull it out of thin air, because I'm doing work on one end with this force, which is a small force, but then on this end, we're getting a big force, which is also doing work. And so is this force doing more work than this force? Is it doing more work than this force? Is F2 doing more work than F1? What do y'all think, yes or no? No, it can't, right? Because there's no energy being transferred there. The difference, the answer is no. The difference has to do with, well, how we think about work. That work is equal to a force times a displacement. So on this hydraulic lift, I have this small force, acting over a big distance. And then over here I have this big force acting over a small distance. You ever use the hydraulic lift to lift something heavy? Right? You move the handle up and down and up and down. You move it a big distance, but the hydraulic lift just barely creeps up. And so I'm getting a bigger force out, but it's moving over a much smaller distance. That's generally true for simple machines, right? Like, for example, the bicycle, you put in a big force, but then you get a smaller force, but it's applied over a very large distance. That's true for levers, too. All right, so you can think about the work 1 is still equal to work 2 because I put in a small F1 over a big distance, D1, but I get out a big force, F2, over a small distance, D2. And so I'm still producing the same amount of work. It's just my displacement is different for the differing forces. But nonetheless, it's useful because it allows you to lift heavy things. Let's see, do I have a particular question about this? No, let's look in the back. We'll do a couple of practice questions on the old test, because you'll certainly see one like this. Oh, here we go. Let's do number 17. This is a hydraulic jack. It gives you some of the forces and the areas. I want to know the force exerted by the piston on the right. This is exam 4, number 17. All right, let's stop in about 10 seconds. Stop at 1:45. 1:45. Go ahead and do number 16, actually. We'll do 16 right after this. Sorry. It's a conceptual question. Okay, good. C is right. And when you know how to do these, they're not that complicated. You're just comparing the force per unit area on one side to the force per unit area on the other side. And in fact, you could look at this without even really using your calculator and say, well, this area is 0.024 and this area is 0.008. So this area is 3 times this area. And so this force has to be 3 times this force. So this force is 25 newtons. So this force is going to be 75 newtons. So C is the right answer. But if you want to work it out, if you want to sort of start with the equation that we have, F1 over A1 is equal to F2 over A2. That's going to be 25 over 0.008 is equal to F2 over 0.024. And then you solve that for F2 and it's equal to 75 newtons. You know, by the way, that it can't be A because that would be the same force. So you could get rid of the A right offhand. But the answer is C. All right. Why did the pig leave the costume party? Because everybody thought he was a boar. Oh, y'all did 16? Let's try that one. Oh shoot, which has the larger density? Did y'all look it up on your table? It's in your equation sheet. But you will have questions like this where you have to refer to those tables. So look in your equation sheet. It should be actually on your equation sheet. Isn't that right, Vivian? All right, let's stop at 105. 105. Okay, so we first want to know, we want to define what our density is. It's mass over volume. And both of these are going to have the same mass, and I want to know which one fills the larger volume. So I want to know which one will have the bigger volume. But if the volume goes up, that means that the density has to go down. So the one that fills the larger volume is the one with the smaller density. Which one had the bigger density? Gold has a bigger density, so that means B is the right answer, the one with the smaller density. Be careful on those. I always like to write down the equation and then think about how the variables change depending upon the other values. But you can certainly see a question like that on the test in a couple of weeks. All right. We'll come back to some of these. Let's go back to our notes. You're going to see a manometer or a barometer as well, although we've already seen this in principle when we're dealing with the straw, because the manometer works a lot like a straw, that you have a difference in pressure which causes the liquid to move up a certain height. So a manometer compares one pressure to another known pressure. In fact, as we said before, that all of our measurements are really just comparing one value to another known value. When we're measuring mass, or when we're measuring time, or any time we're making a physical measurement, we're always comparing two values, one that's known and then one that's unknown. That's why we need to know our standards of measurement so well, because we need to know that known value very accurately. Okay, so the way this works is I have a known pressure over here. So our P sub 0 is our known pressure. And then we have our unknown pressure over here. You might have used a manometer before. A barometer is just a specialized case of a manometer. First thing you want to do when you think about this is you want to ask yourself the question, what is the relationship between P and P naught? So I'm going to ask you that for this. Is first, P bigger than P naught? Is P smaller than P naught? Or is P equal to P naught? Let's see what you think about this. Which of these pressures is bigger? This is the liquid inside of the manometer. It's the dark gray. There's some gas here at some certain pressure. And then this is our unknown pressure. Which of the pressures is bigger? Or which of these relationships is correct? P bigger than P naught, less, or equal to P naught? All right, let's stop at, okay, I'm going to show you how to do this. Well, let's stop at 1 minute. 1 minute. All right, so in this case, P is less than P naught, so B is the right answer. Let me show you how, and there are really only 3 scenarios for you to consider, so I'll sketch those out for you. I like to think of having 2 people pushing on either side, and I have one person pushing down on this side and another person pushing down on this side. But the one that's pushing harder is going to push it down farther, so this guy is pushing down hard, and it forces the level of the fluid up over here. Let me show you all 3 scenarios for a manometer. It'll be important when you're calculating the actual pressure, or the unknown pressure. So we have 3 scenarios. Say this is our manometer. It's a tube that is open at both ends. So these are 3 different manometers. And then they're filled with fluid. We'll call this one P naught, and this one P. P naught, P. All right, in this case, what kind of equality or inequality do I put? They're equal, right? They're equal because I have these 2 levels of the fluid are at the same height. And so these 2, P naught and P, are equal. What about here? Is P naught bigger or smaller than P? It's smaller because this level of the fluid is higher. So this pressure is just not pushing down as hard as this pressure. This one's pushing the fluid down and forcing it up over onto this side of the tube. It's the same with the straw, that you create a slightly smaller pressure here, and then the atmospheric pressure pushes it up into your mouth. So that's like a straw. And then here, P naught, this pressure is bigger or smaller than this pressure. It's bigger, right. So my signs would look like this. I'd have an equal sign. I would have a, which one was this one? This one is smaller, and this one's bigger. So this one's like a straw, and then this one's like a straw in reverse, like when you blow bubbles in your chocolate milk. Do you ever do that? You don't drink chocolate milk anymore, do you? Like that's just, do you? Listen, we got some of that Promised Land chocolate milk. It's like melted ice cream. Ever had that at the grocery store? It's very good. But we don't get it that often. But then I told my kids that one day, I think it was one of you people actually. It might have been some other class. But one day I saw this guy that was walking around just with like a half gallon of Promised Land. Was that you, Ethan? No. Who was it? Yeah. Who? Who was it? Oh yeah, it was Cameron. Yeah. So, but when we're at home, like the kids, when we pull out the chocolate milk, they get like a glass this size. Because it's not very good for you, right? It's really bad for you. They were blown away by that. That he would just walk around drinking a whole gallon of chocolate milk. You can tell Cameron that I said that. Okay, so we calculate this pressure like this. The pressure P is equal to P naught, our comparative pressure, plus or minus rho GH. All right? So it depends whether you use plus or minus. Rho GH, right, that's just sort of the pressure due to a column of liquid. We've already seen that. So like, for example, if I have a point right here, the pressure here is equal to rho GH. Remember we developed that expression or derived it last time. I'm walking around with a column of liquids or a column of fluid sitting on top of my head, and it pushes down with a certain pressure just due to the weight of it. And then a similar thing here is that if I determine the pressure right here, it's equal to rho times G times H for this particular liquid. So we want to think about, is this plus or minus? So for example here, well here P would be equal to P naught because H is equal to 0. Here, H is this value, and so since P is bigger than P naught, P is going to equal to P naught plus rho GH. And then over here, P, since it's smaller than P naught, is going to equal to P naught minus rho GH. You know, don't memorize those, but just think about, well, is P bigger or smaller than P naught? Because you'll probably have a question that just asks that as well. Is P, how do these two pressures compare? But then you'll also have to calculate the pressure for a manometer. Okay? Let's do a quick example. I'm just going to sort of sketch it out here over on the side. So let's say that I have a manometer. It's an open tube with two pressures on either end. It's filled with fluid. And the difference in the height of these two fluids is, say, 2 centimeters. And then let's say that the fluid is mercury. So this is filled with mercury. The density of mercury is on your equation sheet, but the density of mercury is pretty big. It's 13,600 kilograms per cubic meter. And remember, that's compared to water. Water is 1,000. So this is almost 14 times the density of water, mercury. So it's 13,600 kilograms per cubic meter. And I want to know what is P. So let's say that this pressure over here is P, and over here I have my pressure P naught. And we'll just say that P naught is equal to 1 atmosphere. And I say, what is P? If P naught is 1 atmosphere, what is the pressure P? Okay? So the first thing you want to do is ask yourself, well, is P bigger or smaller than P naught? And the way the fluids are arranged, which is it? Is it bigger or smaller? It's a bigger pressure because this pressure is pushing the fluid down and then up into this column. So this pressure is bigger. So I'm looking at this situation where P is bigger than P naught. And so if I want to know the pressure, it's going to be equal to P naught plus rho GH. Remember, atmospheres is not our SI unit. Atmosphere is a non-SI unit, and it's equal to 1 times 10 to the 5th pascals, plus the density, which is 13,600, times 10 meters per second squared, times H, which is 2 centimeters, which is 0.02 meters. And so that tells us our pressure is going to be a little bit more than an atmosphere. Atmosphere is pretty big pressure. It's 103,000 pascals. Or, 1.03 atmospheres. Okay? We'll do a sample problem soon for y'all to practice, but you'll certainly have to do that on the test. You'll have to calculate. I'll give you a manometer with a certain reading, and you'll have to tell me what is the pressure in that manometer. You'll have to go through these steps. You'll first ask yourself, okay, well, is this bigger or smaller than the comparative pressure, the pressure that we're comparing it to? And then be able to determine the density of the liquid. That's on your equation sheet, and then calculate the actual pressure. You'll probably use manometers at some point. No, okay. You use manometers at some point, whatever field you go into, to determine pressure. In the health sciences, of course, measure blood pressure. It's a type of manometer. Okay? That's why you measure it in the height of that column. It's millimeters of mercury or whatever. That's actually using it as a unit, whereas just the height of the column. Okay. Let's look at the barometer. The barometer is very similar to the manometer. The only difference is that the pressure, the comparative pressure, is equal to 0. It's a vacuum. So it's the same as the manometer, except the known pressure is equal to 0. Oh, I'm sorry, it's equal to 0. Let's consider this barometer. Barometers are usually filled with what? Any idea? With mercury, right. That's why one of the units for pressure is millimeters of mercury, mm of Hg. Y'all probably seen that before. 760 millimeters of mercury, that is 1 atmosphere. Because if you have mercury in a barometer, it pushes that column of mercury up 760 millimeters. Not that much, right? 760 millimeters, that's only about that far, about 7.5 centimeters. But let's think about a barometer that has water instead. So let's write this. Barometers usually use mercury. And think, oh, the unit millimeters of mercury. That's actually a unit for pressure. But what if this barometer was filled with water? And I think actually further down the page I asked this question, but let's do it here. So what if this barometer is filled with water? What is the height of the column? All right, take just a moment. I'll give you a head start. I want you to calculate the height of the column giving this barometer with a pressure here. Well, what would this pressure be if it was in this room? It would be 1 atmosphere, right? It would be at 1 atmosphere if we were at sea level at 1 atmosphere. Well, what would the height of the column be if we were at 1 atmosphere? Okay. What is the height of this column if it's filled with water? Okay, so I would say that P is equal to P naught plus or minus rho GH, although, with the barometer, this is just a special case where this is equal to 0, so the plus or minus is kind of irrelevant. So P is equal to rho times G times H. I know P is 1 atmosphere, which is 1 times 10 to the 5th pascals or newtons per square meter. And then that's equal to the density. Oh gosh, what's the density of water? Oh, right, it's 1,000. It's 1,000 kilograms per cubic meter. Isn't that remarkable? If you had a cubic meter of water, it would have a mass of 1,000 kilograms. That's heavy. And 1,000 kilograms, that's like a car. It's a heavy thing. All right, so anyway, 1,000 kilograms per cubic meter. G is 10 meters per second squared. And then H, I want to know what H is. So 100,000 divided by 10,000, H would be equal to 10 meters. Remember on that Veritasium video that we watched the other day? What did they say was the theoretical limit of the straw? What's the longest straw that you can have? What's that? Yeah, 10.3. So that's where this comes from. That the longest straw that you can have is if you create a perfect vacuum, because you can't have less than a vacuum inside your mouth. You can't have anything, you can't really approximate a vacuum, you can't get that close. But if you could produce a perfect vacuum, then the height of the column would only be 10 meters, or 10.3 if you use 9.8. Right, so that's where that comes from, that it's like a barometer. If you were able to have a 10-meter straw, you'd have a barometer sucking up water into it. It would only be able to reach 10 meters, because that's the atmospheric pressure. Now, if you were at a higher atmospheric pressure, then you could have a longer straw. But, there's no place to get a higher pressure in nature anyway on Earth. All right. Why do we use mercury then instead of water? Because mercury is pretty toxic, right? And so we wouldn't really want to use mercury. But the reason that we use mercury is because of this, that at 1 atmosphere, the column of mercury is only 7.5 centimeters, or 7.6 centimeters. You know, 760 millimeters. But water, our wine, the very first barometer that scientists built, I forget his name, it's like Torricelli or something. It was made with wine. He tried to make it up with wine, but it didn't work very well. But water is the height. But for water, the height is 10 meters. And that's just not practical to have a 10-meter tube of water. And then also it's very difficult to create that vacuum with such a large column of water. Okay, let's try this problem on the next page where you're comparing two pressures in a manometer, very similar to the question you'll have on the test. You could probably find the answer to this question with just thinking about the answers that are obviously wrong. Or maybe not obviously, but look at the choices and ask yourself, which of these can't be right? Which are just not reasonable? All right, let's stop at about 10 seconds. We'll stop at 3 minutes. 3 minutes. Just 5 more seconds. Okay, B is right. And again, we can look at the options. Just ask ourselves, which of these pressures is bigger? Is the pressure of the methane on this side bigger, or is the pressure over here? Now I know the pressure over here is 1 atmosphere. It's 100,000 pascals. So is this pressure bigger or smaller? Well, since this column of liquid is up higher, I know that this fluid, or this pressure, is not pushing down as much as this pressure. So this has the smaller pressure over here. Let me write that. So I know that if I have my pressure on this side, which we're calling P naught, and then I have the pressure over here, which we'll just call P. I know that P is less than P naught. And once I find that, well, let's see. Well, this is 1 atmosphere over here, so I can get rid of that, and that. So I don't even really have to do any math, per se. I've just done math in my head comparing the two numbers. But then if I really want to double check myself, I can say P has to equal to P naught minus rho GH. Minus because of this inequality here. And so that's going to be 1 times 10 to the 5th minus the density, which is 13,600. That's for mercury. I gave it in the problem, but probably on your test I will not give it in the problem. You'll have to look at the table, look it up. Times 10 times the height of the column, which is 0.05 meters. Make sure that you can do your centimeter conversions quickly, okay? It'll help you on the test. To do centimeters to meters, you just go over 2 decimal places, because it's 100th. A centimeter is 100th. Oh, goodness. I'm having calculator issues. Anybody else want to drop theirs? Are you ready? Okay, good. Yeah, China. No, I mean, it depends if it's bigger or smaller. So if P is smaller than P naught, if this number is smaller than this number, then I know I have to subtract this term. But if it's bigger than that number, then I would have to add this term. So you just want to ask yourself, well, is P bigger or smaller than P naught? If this is smaller, as it is here, then you subtract it. If it's bigger, you add it. Okay? All right. And so this works out to be, I think, 93,000 that we said it was. Isn't that right? Yeah, 93,000 pascals, or we could say that that's 0.93 atmospheres. Pascals, atmospheres. And you should be prepared to give it an either answer. I'll ask you some questions in atmospheres and some questions in pascals. But remember, when you're solving the problem, your numbers always need to be in SI units. That's pascals. In fact, you can never go wrong with SI units. You'll always be right with SI units. Just make sure that your answer is in the appropriate units. That you're looking at the units of the answers. Okay. Let's look at Archimedes Principle. Y'all saw this in lab a little bit. A submerged object experiences a buoyant force. Y'all saw this in lab when you did the cylinders on the rulers and then you submerge them in water or alcohol. Yes? Maybe? Okay. That's buoyant force. A submerged object experiences a buoyant force equal to the volume, or excuse me, the weight of the displaced fluid. So imagine that I have an object that is submerged underneath water, submerged completely. We'll say that it's water. This object displaces an amount of fluid that's equal to its own volume. Alright, so this thing has a certain volume V. When I put it into this fluid, there was fluid here before, and it pushes it out of the way and takes the place of that fluid. So it displaces a certain volume of fluid that's equal to its own volume. And that's why in that lab y'all did the volume by displacement. That's when you've done this, I'm sure you did this in high school probably, where you take a regularly shaped object and you take a graduated cylinder and you look at the level of the water, 50 milliliters, which is a cubic centimeter, or 1 milliliter is 1 cubic centimeter, or 1 cc. 50 milliliters, you drop it in, and it goes up to, say, 73 milliliters, and that tells you that the volume of your fluid, or your object, is 23 milliliters, or 23 cubic centimeters. Y'all know what I'm talking about? done it before high school, probably, maybe middle school. Okay, so that's how we do volume by displacement. It displaces an amount of fluid that's equal to its own volume. And if fully submerged, we'll see a case where it's not fully submerged soon. But if it's fully submerged, the volume of the fluid is equal to the volume of the object, the volume of the displaced fluid. Now, the buoyant force, by Archimedes' principle, is equal to the weight of the displaced fluid. So in equation form, we would say the buoyant force, Fb, is equal to the weight of the fluid. I mean, Archimedes did this, or legend has it that he was trying to figure out, was this crown real or whatever, or some sort of golden thing, and he measured the buoyant force, and by that was able to determine the density of the metal. And then he jumped up and ran naked through the streets, shouting "Eureka" or whatever. Y'all heard the story? Did I get it right? Yeah. Okay. So anyway, this was the idea that he was dealing with. He probably wasn't in the bathtub. I don't know. Maybe he was. But anyway, the buoyant force is equal to the weight of the fluid. So I can write this further. The buoyant force is equal then to the mass of the fluid times g. Now remember that density is mass over volume. So mass is equal to density times volume. And so I can replace this mass right here with density times volume. I don't usually require you to know the derivations, and I'm not going to require you to know this derivation, but it is useful to understand these relationships between mass and density and volume as it pertains to the buoyant force. And so this is equal then to the density of the fluid times the volume times g, the buoyant force. And then that's our expression for the buoyant force. It's equal to the density of the fluid times the volume of the object times g. Be careful, because sometimes when we're working these, and I'll show you, I might have an example, but sometimes the volume, the fluid and the object's density are both given. And you have to find the volume of the object by looking at its density first. Okay? So just be clear that this is the density of the fluid times the volume of the object. Not the density of the object. Like it does matter, but it's not directly relevant here. Times the volume of the object. So density of the fluid, that's the displaced fluid, times the volume of the object. Let's do a quick question. Let's do some questions in the back, and then we'll come back to this. Butterfingers today. Now I only have a couple. Yeah, so exam 4, number 11. I think y'all can do it. It's a little bit different. It'll be a good learning experience. You'll do your best on it. Number 11. And then if you finish that one, start thinking about number 12. Both of these are kind of difficult questions. The first one's just asking you to find the water line of the boat. You have this rectangular boat. It gives the area, which is 2 meters squared, 2 by 1. And I want to know how deep does it submerge. So in this problem, you're going to have to find the volume, the submerged volume of the object, which is the boat in this case. I'll remind you what Archimedes Principle is. It's rho vg, density of the fluid, volume of the object, times g. And then don't forget that the volume of a rectangular prism, which is what this is length times width times height. And I'm looking for height, or depth in this case. The water line. Where's the water line on this boat? There's one other idea that you'll have to connect. All right, let's stop at 3 minutes. 3 minutes. 10 more seconds. Have a mistake in this problem? It doesn't seem like it. All right, let's see. I think it's C. Let's see though. Okay. All right, so my buoyant force, well, how do I find my buoyant force? Like, that's sort of the missing element here, is what is my buoyant force for this boat? What is the buoyant force? It's equal to the weight of the boat, right? So if I have my boat out here in the water, I have a weight that's acting downward, and then I have a buoyant force that's pushing upward. I know that this buoyant force has to equal the weight of the boat, because it's not sinking all the way to the bottom, and it's not shooting up out of the water. But my buoyant force is equal to the weight. And so I also know that the buoyant force is equal to the density of the fluid times the volume of the object. That's the submerged volume of the object times G. And so the buoyant force is equal to 500 kilograms times 10 meters per second squared. That's just to say that the buoyant force is equal to the weight, and the weight of the boat is 5,000 newtons. The density of the fluid is 1,000. The volume of the object is 2 by 1 by the height in cubic meters, and then G is equal to 10. So my 10s cancel here and here, and I get 500 equals 2,000 H. So H is 5 over 20, which is 1 over 4, which is a quarter. So the answer is C. We have we're going to do one more question, but on Friday we'll come back and we'll work some other problems. There's a problem in your workbook too that's very similar to this. But I would expect to see something like this on the test, where you have to calculate some attribute of this object, whether it be the buoyant force or the volume or some dimension of it, like in this problem. Let's look at number 12. We'll see this problem again later. You have a big chunk of steel that's in your boat, and you take it and you throw it overboard and it sinks to the bottom. What's going to happen to the water level in the lake, like with respect to the shore? Is it going to rise, drop, stay the same, or does it depend on the mass of the steel? I'm going to remind you that the buoyant force is equal to the weight of the displaced fluid. And so you want to ask yourself, the question is, when does the steel displace more fluid? Does it displace more fluid when it's in the boat or when it's on the bottom of the lake? And the time when it displaces more fluid is when the level of the lake is going to be biggest. Let's stop at 110. Okay, good. Let me explain, because we didn't do that great. But, so imagine I have a lake, and I have a boat, and there's a piece of steel down in the bottom. That steel is displacing a lot of water. It's displacing its own weight in water. But if you have steel, if you take the same amount of mass in water, you have more water because it's less dense than steel. So when the steel is in the boat, it looks like that. But when the steel is out of the boat, the steel is sitting on the bottom of the lake. The boat actually goes up, and then the level of the water actually goes up as well. So the answer, no, I'm sorry, the boat goes up, and then so the water actually goes down because it's not displacing as much water. We'll see that question again. We'll talk about it more later. Why don't we wrap up there? Y'all have a good day. I'll see you on Friday, okay?